This is IAT355 Visual Analytics, Lecture 7.2, where we're going to talk about cautionary tales. In Lecture 7.1, we spoke of Tamara Munzner's marks and channels, and what we're going to talk about now is ways in which you can misuse or mistakenly use certain channels, particularly those of color, in ways that kind of disrupt the goals that you may have of truthfully representing some underlying piece of data. So let's get started. So one of the first and kind of most salient mistakes that you can make is to mistakenly map color. And one of the key ways to mistakenly map color is through the use of what's called the rainbow color map. And the rainbow color map seems to be innocent enough. Here in this depiction here of the state of Texas, we have the range of colors going from a low wavelength of, high wavelength of red down to a low wavelength of purple. And it goes red, orange, yellow, green, blue, indigo, violet. Although this seems more towards red in this particular variation. And the reason why that's appealing is there's a kind of a mapping to, to the number of nanometers of wavelength of the individual colored light. There's a drawback, though. First off, as we've said a few times already in the course, that each step, say by 10 nanometers, is not perceived as a difference of a certain amount of color. Small changes in wavelength in the domain of green are viewed as very significant changes in perceived color, whereas small, equally sized changes in blue are indistinguishable from each other. So this color map of the map of Texas has that problem. In particular, there's a lot of purples and blues in this state, which stands for around the 75% region, and you can't really tell whether it's sort of 55% up to about 85% because they're all looking fairly similar. So there's always a concern whenever you see color maps. Part of the motivation is that the rainbow, by mapping to spectral colors, seems sciencey. But there's a drawback, and that is scienciness isn't the mandate, isn't the figure of merit. What matters is the perceptual salience of small changes in color and small changes of wavelength, leading to large perceptual changes in color. So that's something always to watch out for. So it turns out there's a few fields out there that tend to use the rainbow color map a lot. Typically, weather maps use color quite a bit. There's been some refinement over the years, particularly the publicly accessible weather maps. But here's an example. This is from a website, windy.com, which we will get to in a bit. And here, what this thing does is depicts wind flow all over the world, picked up probably from weather buoys and that kind of thing. And you can also show color and satellite imagery and so on and so forth. And one of the really nice things it does is depicts wind flow by moving arrows, and we'll show that in a sec. But here, you can see that there's some color bands that are associated with KT, that's knots, or that's wind speed and the nautical measurement knots. And there's a big difference, apparently, in the speed on the yellow side of this blob to the green side. But if you look at the scale, you can see that yellow is roughly about 20 knots and green is about 15 knots. So the big blob here that looks really like a big change is not a big change at all in terms of the actual weather. So what I'm going to do now is I'm going to go to windy.com, and here it is. And so as you can see, it's kind of got this nice display of wind blowing around in the Eastern Pacific. And there are two weather systems at play here. They're not marked, but you can kind of infer there's, I think, possibly a low pressure area centered right here, and a high, another low centered roughly over Hawaii, and each one of these things is causing clockwise flow. Don't quote me on whether it's a low or high, but there's an extreme in one direction, either high or low in each of those two spots. And what happens is that the wind flows clockwise around these features. So this thing that we see here, this boundary, you can see that this is a real feature. That is to say, wind flows, kind of like southwest on this side of that boundary, and northeast on that side of the boundary. And right along the boundary is an area, a very narrow domain of net wind speed to be very low. It's not, a dangerous situation. It's just where the two weather systems interact. There's a boundary there, and so that kind of blue stripe along there indicates, there's a really serious feature there. However, there's also a visual feature up here, but once again, the difference in values from here to here, you can see that the wind arrows are not changing in character here at all, but there's the green area and the yellow area, and the yellow area is really indicating visually that something salient is happening here, but because of the poor color choice, it's not a real feature. Let me just now go to temperature, and we can see a similar phenomenon. So once again, there's that, this is actually a frontal boundary. There's a serious feature going on there, and the temperature is not too much different on each side, whereas if we go over to southwestern Alberta, you can see there's a big temperature color change going on here. Sorry, temperature color change going on here. That is, a very small difference in temperature. It's 10 degrees, to 15 degrees to 20 degrees. You certainly could feel that difference because that's degrees Celsius if you drove from, say Edmonton to Jasper National Park. But the actual difference in temperature is not that great. Compare that to the salience of this thing, where there's a big difference from green, kind of, single-digit temperatures, to below freezing, -10. That's a real feature. This is less of a salient real feature. That's particularly a strong feature to care about, simply because it's going from above freezing to below freezing, and that's a very important feature that you shouldn't hide. And so what that is kind of an illustration of the ways in which you can make mistakes in terms of mapping color. Here's another one in which the rainbow coding is not really doing the viewer any favors. So this is another rainbow color map applied to actually a climate phenomenon, and this is about an estimated fraction of precipitation lost to evapotranspiration. That is to say, rainfall hits the ground and evaporates somehow or other. I don't know the exact details, but what's the key feature here? Well, there's a key north-south feature running from western Minnesota all the way down to Texas. And it looks like there's a big difference between the light green and the dark green here. There's also a big difference here between the orange and yellow, and of course big differences here, in the Pacific Northwest and elsewhere on the map. But the drawback with that is that this pseudo feature here, that's yellow, 0.9 to 0.99, and versus light green. Sorry, mid green is 0.8 to 0.89, and dark green is 0.7 to 0.79. So a very small difference. Each of these color bands is responsible for 1/10, and one of the biggest differences that's depicted on the map is this significant change in luminance from the dark green to the greenish yellow to the yellow. And in fact, there's just as big a difference from this chunk to this chunk as there is from this chunk to that chunk, except they look totally different in terms of the visual mapping. So this is the kind of thing that you have to watch out for, and the particular warning sign is if the mapping to color has a big difference from neighboring values in terms of luminance. And so what goes on is that the rainbow color map, mixes changes in luminance along with changes in hue, puts that all together, and that luminance and hue combination, particularly around yellow, really makes visually salient things that are not really present in the map. So another way in which you see color maps used is by using ramps that are more restricted in hue. So in this one, this is from Tableau, what we're doing is showing a sales feature for office supplies, furniture, office supplies and technology, and this is in one of their sample data sets. And what we've done here is mapped color to a continuous ramp and the values that are mapping to color range from negative 4,000 in terms of profit to 27,000. So it's a skewed data set with a strong skew in the direction of big money. And what this is showing you is, yeah, there's a range, and possibly the smallest value is around here for consumer in the central region for furniture, and the largest value is this one down here, again, consumer in the west for technology. But the problem is because we're not all that good at transforming luminance values, because this is just luminance or brightness, transforming that into numbers that have been used for the mapping. Slightly better is this one here, but what's happened is that there's a double-ended color map, and the center point of this map, sort of neutral colors, is as close to neutral colors, is placed at the median. And so we can see that there are a number of locations which are positive, and those are in the green domain, and a bunch of other stuff is below that median, and this one is the most strongly below the median. The drawback with this one, though, is that red-green color blindness is one of the more common color blindnesses. So this one is probably not so strongly preferred as this one here, in which instead of green, we're using blue for the upper range. It's the same, roughly the same mapping, but the intensity of blue is being used. And what's happening, of course, is that we're visually quantizing all of these things into separate swatches. They're not quantized in the ramp, but we're likely to perceive those things as quantized swatches of color. Here, what we're doing is remapping the color map such that 0, the actual value of 0 in the data, is mapped to this neutral gray color, and negatives get reds and positives get blue. The other thing that we're doing is we're mapping kind of even values of extremes. So the darkest blue is mapped to 27,000, and the brightest, the most intense red will be mapped to negative 25,000, except the values don't go to that negative a number. So we just have again, the least value is located right here, but it is mapped to a more subtle pink color. Here's a situation in which we're using the full color range. So we can see once again that 0 is at gray. There's a slight negative value here. There's a slight touch of red in this one, and these two squares are at the most negative, and this is of course the most negative, but that doesn't mean it's negative 27,000. It is mapped to negative 3,993. Here, what we're doing is, instead of mapping to a continuous range of color, even though we perceptually quantize it, we're doing the quantization in the color ramp and quantizing equal sizes of the range to around 0 to 5,000 to 10,000, etc., all the way up to 27,000. And you can see that this again depicts a little bit of a different layout with respect to the stores and the product areas that are not making much money compared to in the consumer technology space, which is making a lot of money, and you can see that more readily in this map. Finally, this color map is just mapping to just 2 colors, and that's because there's no that's been a data remapping. If the value is negative, it maps to -1. If the value is positive, it maps to +1. And if it's 0, it maps to 0, but there's no actual 0 values in here. And so in this binary encoding, or ternary if there was a third color, clearly shows where money is being lost, and everywhere else money is being gained. But of course, what you're losing in this is the depiction of the quantity of profit, because at the data level, the data mapping is just projected out that information. It's disappeared because we're just mapping to plus and minus 1. So another way in which we can use color is, as we mentioned in the previous lecture segment, is to do various other types of tasks, and one of them is to separate items. And so here, again from Tableau, is a mapping in which what we're trying to do is to maximize the separation of each of these line graphs. So we have red, green, blue, and orange, not yellow. And these are not exactly the same luminance, but they're different enough from each other that they separate from each other. These other two also perform the task of distinguishing the 4 line graphs from each other. And each line graph corresponds to a quarter of the year, a 3-month period throughout the year. On the right, we can see, just one second. On the right, we can see that, again, the quarters have been mapped to colors, but instead of being distinct colors, what's happened is each quarter is mapped to 4 steps in a single hue color map where we're controlling the luminance. The most luminance or brightness is at quarter 1 in this one, and so the lightest one is Q1, then darker, and the darkest one is Q4. The same thing is happening here, except we're not using blue. We're just using essentially monochromatic color. In this last one, we're using color in a different way. What we're doing is we're using color to highlight an anomaly. That notion of there being an anomaly or an outlier of some kind is, comes from outside the system. We're just simply showing that somehow or other an anomaly, something that needs to be paid attention to, something weird is going on with the quarter 4 results. I'm not speaking to what that weirdness actually is. So, other things to bear in mind that are of some concern is that when you're using shape, you can have sort of generic geometric shapes in which we differentiate things like curvature and sharpness. But one of the things always to watch out for in the use of shape is that there can be other meanings that we bring to the table, and it's always wise to watch out for what those other meanings may be. So this arrow shape, for example, might depict there's some kind of relationship from something to some other thing. The from being at the tail end of the arrow and the to being at the head end of the arrow. Other things, other shapes are often used to relate metaphorically to some other concept. So this green leaf is something that might be eco-friendly or something like that. And if you're using green leaves and other kinds of shapes, an oil can or something like that, you're doing a bunch of things if you're using those in your depictions. One of the things, of course, you're doing is differentiating among things according to their shape, but you're also bringing to the table the values of whatever that shape or depiction calls to mind. So this is calling to mind organic versus oil-based or something like that. These two here are similarly acting in an iconic way to bring meaning in addition to whatever is being used to distinguish one mark from another. This meaning, this iconic description of the globe indicating the world somehow or other. This thing indicating disability or something like that. Both of those things are not only being used to distinguish one shape from each other, but also bringing more meaning than say a square, circle, and triangle would by themselves. So if that's what you mean to do, then that's great, but you should always take some care not to do that accidentally and have that be part of your rhetorical toolbox that you're intentionally deploying as opposed to, kind of making a mistake in some ways. One of the things always to watch out for, particularly with shape, is that we kind of have a limited shape vocabulary. And part of that is due to, we can perceive shapes, particularly if they're large, but, if they're small, and particularly if there's a lot of repetitions of the individual shape, and we'll show an example of that in a sec, we need to be able to link what that shape is to something else, perhaps to a name or something like that. So those icons that we showed on the previous slide, the world icon, the leaf icon, those things have, a connotation of, eco-friendly and that kind of thing, but they are easy to remember due to, repeated use in our culture. So we need to take some care there. One of the other things that tends to happen is that shape and size of things tend to interact with each other, and the smaller the object is, the harder it is to decode relative values. So here we have a pie chart, one of our favorites, right? And those very small pie segments, this particular one here, BLMN, it's very hard to tell what size that thing is. And it's, of course, drawn very small, but it's makes it difficult to depict the value because it's so small and just barely perceivable. The other thing is the more complex the shape, the number of sides to it, the harder it is to decode as to what it is. And of course, that depends on the size of it. If it's a big thing, then it's fine, but the size of, say, each of these individual boxes. But if it's small, approaching the size of this red slice here or smaller, then you're really asking for trouble. You're also asking for trouble with those small things to be able to pick off the color. I think it's red, but it might not actually be red, but that's just the color that seems to come to mind for me. So an example of that is, these two plots here where we're using the same shape throughout this scatter plot, plotting service metrics against some other measure. And when they're all the same shape, then really what we're doing is trying to use color to pick off what is going on in this scatter plot. Here, shape had been mapped to an individual quarter to something that is ordinal, fundamentally ordinal, and mapping this kind of ordinal data to a shape is, in my opinion, just really making it difficult to comprehend what's going on. It will be fine if you're trying to pick off the triangle in which the point goes to the left as if it were an arrowhead or something like that. But when you're trying to distinguish from other shapes, and particularly if they're all overdrawn quite a bit as they are in this diagram, then yeah, that's very challenging to decode. And when you're doing visualization, you'd rather not put your user in the situation of having to decode and understand what's going on in your visualization. So the next thing I wanted to point out is we had said in lecture 7.1 that we can use angle for certain things, particularly to distinguish marks. The capacity there is fairly limited. You can sometimes do a little bit better if you're using angle in the context of something. This is, say, in a radial gauge type of environment. But it really works the best when that scale is present, as it is here. It's kind of an unintense scale. It's not marked to a great fine detail. And if you're using the same scale a lot. So the speedometer in your car is an example of that kind of thing. If you drive the same car every day, then you're used to looking for where the needle is and having that correspond to the speed you're going and understanding it from that situation. And most cars have speedometers that have the same kind of range, unless you're driving a supercar or something. But if you change cars every day, or had a different dial meter in every single car, and it was radically different, then probably your ability to rapidly figure out what speed you're going would be somewhat diminished because of the changing geometric substrate in which that quantity was being depicted. Lastly, one of the things that can be very hard to understand is the use of 3D, and Munzner goes to great lengths to point out, as a rule of thumb in chapter 6, that please no gratuitous 3D. Now, I had done some research on 3D, so I would possibly be expected to object to that, but by and large, she's right. And as I said, actually in lecture 7.1. One of the things that makes 3D very hard, particularly when the depiction is static the way it is in these slides here, is it's very hard to detect the shape and kind of unpack that 3D-ness of the shape from the area it's intending to depict. And so here we see a 3D pie chart, and the 3D, the tilt here, it's not orthogonal to the screen, but it's tilted back in some ways. And so you then are faced with the problem of figuring out whether this, the red sector is the same size as the blue sector, or perhaps the purple sector. They look roughly the same size, but there's this perspective distortion in that because this is closer, it's going to be larger because it's closer to the camera. This thing's farther away from the camera. So is the fact that this thing is smaller, it means that the data is smaller, or just that it's far away? And that's one of the problems with 3D, is that ambiguity creates this perceptual, visual ambiguity creates this perceptual and understanding ambiguity, and that's not doing you any favors with respect to doing visualization. So this has been a kind of a brief list of cautionary tales, things that you should watch out for if you find yourself doing visual analytics and feel perhaps tempted to use, whizzy graphics figures. The stuff we talked about in section 7.1 and the perceptual aspects in lecture 6 are attempt to get at the issue of what's going to be reliable as a means of turning numbers into pictures, so that the pictures that the user sees are transformed into the same numbers in the user's mind. That's the task that we're always trying to accomplish in visual analytics, and that's a thing that we need to be able to do as well as we possibly can.